Greetings and welcome to lecture number 7 on the course Introduction to Fourier Analysis. We are in the middle of examining the relationship between the smoothness of a function and the decay of its Fourier coefficients. We concluded the last lecture by defining weak derivatives and proving theorem 2.4. The nth Fourier coefficient of the weak derivative of a function f is given by multiplying the Fourier coefficients of f by a certain polynomial in n. It follows from this formula and the Riemann-Lebesgue lemma that the Fourier coefficients of a k times differentiable 2π periodic function decay like the absolute value of n to the power minus k. We just briefly mentioned this result at the end of the previous lecture, but let's now see all the details in the form of a corollary. Assume that f is a 2π periodic k times continuously differentiable function. Then there exists a positive constant c such that the absolute value of the nth Fourier coefficient of f is bounded by c times the norm of n to the power minus k. To prove this, first recall that the classical derivatives of f are also weak derivatives. So, for any multi-index alpha with order at most k, the function f has a weak alpha derivative d alpha of f in L1 of t. Now, for any such multi-index alpha, we deduce from theorem 2.4 that the limit, as n tends to infinity, of the absolute values of the nth Fourier coefficients of f multiplied by the factors absolute value of nj to the power alpha j is equal to 0. To arrive at the claim in the corollary, we apply this information to a few special choices of the multi-indices alpha, namely the ones which are 0 in all the other coordinates except the jth coordinate. And the value of the jth coordinate is k. Evidently, the order of any such multi-index is precisely k. Now, if we rewrite the limit above concerning general multi-indices for these special choices, we find that the limit, as n tends to infinity, of the absolute values of the nth Fourier coefficients of f multiplied by the absolute value of nj to the power k equals 0. This is true for every choice of the index j between 1 and d, and we may sum up the results. This way, we finally see that the limit as n tends to infinity of the absolute value of the nth Fourier coefficient of f multiplied by the norm of n to the power k is bounded by the sum of the limits we just computed above, and hence this limit also equals 0. From this observation, it follows that there exists a positive and finite constant c as claimed in the corollary. The absolute value of f hat n is bounded from above by c times the norm of n to the power minus k. This completes the proof of the corollary. We next discuss the converse question. What can we say about the smoothness of a function assuming some decay from its Fourier coefficients? There is an elementary but not very satisfactory result, which we leave as an exercise. We only record the one-dimensional case, and figuring out the correct version in higher dimensions is left as another voluntary exercise. Let f be a 2π periodic L1 function on the real line, and assume that there exists a positive constant c such that the following holds. The absolute value of the nth Fourier coefficient of f is bounded by c times the norm of n to the power minus k minus 2. Then f is k times continuously differentiable, or to be precise, f agrees Lebesgue almost everywhere with a k times continuously differentiable function. As a hint for this exercise, check that the Fourier series of f converges absolutely and defines a suitable candidate for the smooth function with which f agrees almost everywhere. To summarize what we have learned so far, we have now seen that the Fourier coefficients of k times continuously differentiable 2π periodic functions decay like the inverse of the norm of n to the power k. And conversely, the k times differentiability of a function follows from a condition on the Fourier coefficients which is 2 orders stronger than k, namely that the Fourier coefficients decay like the inverse of the norm of n to the power k plus 2. This discrepancy between the exponents k and k plus 2 is not so satisfactory. Next, we will introduce an important new space which can be characterized by a single condition on the Fourier coefficients, although not quite as elementary as the ones we saw just now. This space is called the Sobolev space. The definition of Sobolev spaces involves two parameters, a natural number k, which is at least 1, and an exponent p, which can be anything between 1 and infinity. With these parameters, the Sobolev space wkp of t consists of those 2π periodic LP functions f with the property that all the weak alpha derivatives of f up to order k exist and are also 2π periodic functions in LP. On this course, we only have time to look at the Sobolev space with exponent p equal to 2, that is wk2 of t. This space admits a nice and explicit characterization in terms of the Fourier coefficients, which is our theorem 2.6. Let k be a natural number, at least 1, and let f be a 2π periodic L1 function. Then f belongs to the Sobolev space wk2 of t if and only if the following sum is finite. The sum over all integer d tuples n of the absolute values of the Fourier coefficients f hat n squared multiplied by the norms of n to the power 2k. It might be clearer to read the sum as the sum of the squares of the numbers absolute value of n to the power k times the absolute value of the nth Fourier coefficient of f. Recall that if f was k times continuously differentiable, then the limit of exactly these numbers tends to 0 as n tends to infinity. Certainly, it follows from the characterization in theorem 2.6 that these numbers also tend to 0 for all Sobolev functions in wk2 of t. However, as you may recall from the exercise we discussed before, this conclusion was not quite strong enough to guarantee that f is continuously k times differentiable. So, functions in wk2 of t need not be k times continuously differentiable. Let us then prove theorem 2.6. There is an easier and a harder implication. We start with the easier one, where we assume that f is a function in the Sobolev space wk2 of t. In particular, the weak jth partial derivative of order k in each variable separately is a 2π periodic L2 function. By theorem 2.4, the absolute values of the Fourier coefficients of this function are equal to the absolute values of nj to the power k times the absolute values of the Fourier coefficients of f. Since the norm of n to the power k is bounded by a constant times the sum of the kth powers of the absolute values of the components of n, we may perform the following estimate. The sum over all integer d tuples n of the norms of n to the power 2k times the absolute values of the Fourier coefficients of f squared is bounded by a constant times a double sum, first over the component indices j running from 1 to d, and second over all integer d tuples n of the absolute values of nj to the power 2k times the absolute values of the Fourier coefficients of f squared. As we observed, the terms in this latest sum equal the absolute values of the Fourier coefficients of the jth partial derivative of order k. Since f was assumed to be a Sobolev function of indices k and 2, any such partial derivative is an L2 function, and what we see on this line equals, by the Plancherel identity, its L2 norm. Consequently, the sum is finite, as was claimed in the first implication of theorem 2.6. This concludes the proof of the first and easier implication of theorem 2.6. To prove the second implication, we assume that the sum over integer d tuples n of the norms of n to the power 2k times the Fourier coefficients of f squared is finite. Under this assumption, our goal is to prove that f is a function in wk2 of t. This involves verifying first that f is an L2 function and second constructing weak derivatives of f in L2 of t up to order k. To begin the proof, note that if n is a non-zero integer d-tuple and alpha is an arbitrary multi-index of order less than k, then the absolute value of n to the power alpha is bounded by the norm of n to the power k. It therefore follows from our assumption that the sum over integer d-tuples n of the absolute value of the number n to the power alpha times the nth Fourier coefficient of f is finite. This is true for all multi-indices alpha of order at most k. It is worth mentioning separately that the previous conclusion also holds for the trivial multi-index alpha with all components equal to 0, for which n to the power alpha equals identically 1 for all integer d-tuples n. Indeed, in this case the sum over integer d-tuples n of the Fourier coefficients of f squared is bounded by the 0th term in the sum, namely the 0th Fourier coefficient of f squared, plus the other terms where we may insert the factor norm of n to the power 2k. But the 0th Fourier coefficient of f is bounded by the L1 norm of f, and we assumed in the theorem that f is a priori an L1 function. Hence, both terms here are finite. From this observation and Plancherel's identity, we may deduce that f is an L2 function, and we have already accomplished one of our objectives. It now only remains to construct the weak derivatives d alpha of f in L2 of t. This is based on the estimate star, which should now be interpreted in the following way. Fix a multi-index alpha with order at most k, and consider the sequence of complex numbers Cn, indexed by the integer d-tuples n, and given by I times n to the power alpha times f hat n. By the estimate star, this sequence is L2 summable, or in other words, the second powers of the absolute values of the number Cn are summable. Combining this information with proposition 1.13, which was the Converse Theorem discussed near the end of the previous set of lecture notes, there exists a 2π periodic L2 function g alpha whose Fourier coefficients agree with the number Cn. Hat g alpha of n equals Cn equals in to the power alpha times f hat n. The motivation for defining g alpha this way stems from theorem 2.4 in the previous lecture, which stated that if g alpha happened to be the weak alpha derivative of f, then the Fourier coefficients of g alpha would be exactly the numbers Cn. So, g alpha is a good candidate for the weak alpha derivative of f. To prove that indeed g alpha is the weak alpha derivative of f, we need to verify the following equation for all smooth 2π periodic functions phi. The average integral over the box t of f times the classical alpha derivative of phi equals minus 1 to the power order of alpha times the average integral over t of g alpha times phi. In the sequel, this equation will be called the weak derivative equation for g alpha. To verify this equation, fix a natural number big M and let fm and gm be the mth partial Fourier series of the functions f and g. In other words, fm equals the sum over all integer d-tuples n whose norm is at most m of f hat n times en. The function gm is defined in a similar way. Recall here, once again, that the Fourier coefficients of g alpha equal in to the power alpha times f hat n. The main result which we proved in the L2 theory of Fourier series was that the partial Fourier series of a 2π periodic L2 function converges to that function in the L2 norm. So, in particular, fm tends to f in the L2 norm and gm tends to g alpha in the L2 norm. Now, in order to verify the weak derivative equation for g alpha, fix a smooth 2π periodic test function phi. We would like to show that the following difference is zero. The average integral over the box t of f times the classical alpha derivative of phi minus 1 to the power order of alpha times the average integral over t of g alpha times phi. To prove this, we take the absolute value of this difference and then add and subtract two separate auxiliary terms. The first one is fm times d alpha of phi. The second one is gm times phi. Once these two terms have been added and subtracted, we apply the triangle inequality and find that the first absolute value is bounded by the sum of the following three terms. First, the absolute value of the average integral over t of f minus fm times d alpha of phi. Second, the absolute value of a very similar looking difference as the one we started with, except that both f and g alpha have been replaced by the smooth approximating functions fm and gm. Finally, the third term is the absolute value of the average integral over t of gm minus g alpha times phi. If we first look at the terms 1 and 3, we recognize that the functions phi and d alpha phi are smooth 2-pi periodic functions, and in particular they are in L2 of t. On the other hand, the differences fm minus f and gm minus g tend to 0 in the L2 norm, as we discussed. Now, it follows from the Cauchy-Schwarz inequality that both terms 1 and 3 tend to 0 as m tends to infinity. It remains to consider the term number 2. All the functions appearing in this term are smooth and 2-pi periodic, so we may apply integration by parts to the first term, namely the average integral over t of fm times d alpha phi. The conclusion is that this term equals minus 1 to the power alpha times the average integral over t of the classical alpha derivative of fm times phi. Here, the smoothness of fm was needed to make sense of the classical alpha derivative. Finally, it is a simple computation that the classical alpha derivative of fm equals the function gm. If we plug this result first in the integration by parts formula obtained just above, and then we bring this formula back to the term 2, we see that the term 2 vanishes identically for any value of the parameter big M. We have now shown that all of the terms 1, 2 and 3 are either identically 0 or tend to 0 as m tends to infinity. This implies that the initial absolute value we were interested in vanishes, and hence g alpha is indeed the weak alpha derivative of f. This concludes the proof of theorem 2.6. On the next lecture, the theory of L2 Sobolev spaces we have just developed will be applied to prove a fundamental regularity result for elliptic partial differential equations. This concludes the 7th lecture on the course Introduction to Fourier Analysis.